Alright, so first we state a Cauchy's integral formula in a convex open set. So omega is a convex open set in the compass plane, gamma a closed path in omega. Okay. F. Now F is assumed to be analytic on the whole convex open set. Okay. If Z in open state and Z is not on the path. Okay, so we have this situation. Okay, then we have Fz times the index gamma of Z, okay, is equal to 1 over 2 pi I gamma F plus psi minus Z d psi. This is called the Cauchy's integral formula. All right. So we have convex. So convex open state is like this. We put this. Okay, and we have okay, this is gamma. Okay. All right, and Z here. So Z could be here, or can be here, but cannot be on the path. Okay? Otherwise, the denominator is 0, right? And it is interesting that the f of z, so if f is analytic on the whole convex open state, then the value f of z times the index of z with respect to the cross curve gamma actually can be expressed by a line integral. Okay? So the value actually is determined by the value on the path. You know, f the side run over all points on the path. So the value on the path, all right, okay, will determine the value of z, okay, the value of z, okay, which is not on the path. But of course, if the index is 0, you cannot get the value, of course, right? So you can get the value if and only if that the index is not 0. Index is not 0. So that's why the index is very important to state the Cauchy's integral formula. Okay. All right. So again, I skipped the proof, but the proof is actually in my lecture notes. Okay. So the point is that this is the surprising fact. Okay, this is a surprising fact. So now I state a theorem given in the textbook. Cauchy's integral formula. Okay, in a simply connected domain. Of course, to prove a Cauchy's integral formula in a convex open state, we need a Cauchy's integral theorem in a convex open set. So you use the corresponding theorem in section number 2. Okay. And to prove this theorem, the Cauchy's integral formula in a simply connected domain, we need the Cauchy's integral theorem in a simply connected domain in section 2. So, omega is a simply connected domain in the compass plane, and the gamma is a simple closed path in omega, and which is very important for the orientation, which moves counter clockwise. Right, because we need to know the index. This is because we need to know the index. So we have to specify that. For here, I don't care about the orientation because the index will tell you the orientation. Here, so orientation is already here. Okay? Right, so gamma, and which moves counterclockwise. F is an analytic function on the simply connected domain. So if Z, okay, and Z are in omega, okay. Now, if Z is enclosed by gamma star, means that Z is inside. This is inside of the simple curve path. Then we know the index is 1, as we just showed you, right? The index is 1, so the index is 1, so f of Z can be written 2 pi I gamma psi minus Z would be psi. Okay? So if Z is enclosed by gamma star, then we have this formula. And if not, means that Z is outside of the simple closed path, outside. Now the index is 0, right? So we have, if not, then we have 0 equal to 1 over 2 pi I gamma F so to come to 0. And so now we cannot recover f of Z. We cannot. If outside of the simple closed curve. Okay, so the situation, let me write down the situation here. Just like a Cookie Monster, right? So this is omega here, and you have a simple curve. So you may have that. Okay, so this is gamma star, and then you have point here, Z, or Z here. So you have two situations. Point inside, you have this formula. Point outside, you only have this one. Okay? It's because the index here, and because this is counterclockwise, so this is the orientation. So the index here is 1, the index here is 0. Okay? Yeah. So now, so the statement is quite simple. Right? The Cauchy's integral formula is quite simple. if we understand the concept of index. Okay, so now we'll go to derive, use the Cauchy's linear formula to prove that analytic functions has any order, have any derivatives of any order, right? So this is theorem. I'll just state it directly. Derivatives of analytic function omega, right? So here is open set. My statement is usually general than the statement in the textbook. Okay, I try my best to give you the most generalized result. So omega is an open set, okay, in the complex plane, and z is 0, a point in the open set. Gamma, a simple closed path, okay, in omega. That, right? So a simple closed path in omega that moves counterclockwise. Again, right? The reason why we want counterclockwise is because the index, the reason for the index. Okay, so the simple closed path moves counterclockwise and enclose the point z0. Okay, so z0 is inside of the simple closed path, right? And whose interior, okay, lies in omega. Alright, so this is the situation. So gamma is the simple closed path, so the interior, the whole interior lies in the open set. Right? Now if it's analytical on the open set, then we can express the derivative of the function at z0 as a line integral gamma fz z minus z0 square dz. Okay, so now we can express the derivative of an analytic function, okay, by such a line integral. But you have to select the cross path, which gamma should be a simple cross path. Okay, this is the simple cross path, and the whole interior of the simple cross path must be omega. Okay, and the z0 is enclosed by this simple cross path, and the simple cross path is oriented counterclockwise. Okay. Right. And also we can write the second derivative, and it is interesting. It's 2 factorial 2 pi I gamma. Now it's f of z, and the denominator is z minus z0 cubic. All right, the third power here. And in general, we have nth derivative, right? So we have nth derivative, and this derivative, again, can be expressed by the line integral n plus 1 and dz. Okay. All right, so this theorem right, so this theorem actually is proved by Cauchy's integral formula. Okay, and well, I will give you the detailed proof. Okay. The proof given in the textbook, just go to these steps. Okay, and the general formula, as said in the textbook, is by induction. So I decided to give you how to use induction, right, to get into this formula. Okay, so I will give you the detail of the proof. Okay, and so so I want to say a word about this theorem that the corollary is that if f is an analytic function on an open set, then its derivative is also analytic. Okay? So derivative of analytic function is analytic. So you can do that again and again. Okay? Okay, and so the reason why we can prove that is because we have the Cauchy integral formula. Without Cauchy integral formula, we can't prove this fact. Okay, we can't prove this. Okay. Now the following the estimate of Fn is quite useful. Okay. So in many situations we want to estimate maybe I just say the S derivative of an energy function. Okay, so it's stated here. 14.418. Okay, Cauchy inequality. Sometimes people say that Cauchy's estimate. That's fine. So this is called Cauchy's estimate. Okay, I stated in the most generalized form, if fh is analytic, suppose the function f is analytic on an open disk with center A, radius capital R, okay? And we know that this analytic function has an upper bound for all z in B. Right. So under these two conditions, so f actually is analytic on an open disk with center as A and radius capital R, and we know that for all z in this open disk, the absolute value of the function value is less than or equal to m. Then we can give a good estimate for for the A here. Okay? For the S derivatives of f at point A. Okay, the point A would be n factorial times n divided by r n's power 1, 2, 3, etc. So that is a good estimate. Right, this is a good estimate. Okay, and the proof. The proof is here. So first of all, we fix a positive number r less than capital R. Okay, and the gamma is the positively oriented circle with center at A and radius little r. So the situation is here. We have A here, and this is the big one. The radius is capital R, and we have a smaller one. Okay, the radius is little r, and we have and the orientation is here. So this is here. Okay, so this is our situation. Okay, and the D, A, up. So this part is the disk. So now, gamma. So gamma is a simple closed path. Okay, in this big open disk that moves counterclockwise. Oh, so I have to write down the A plus R E I 2 pi T. Okay, so this is the function, this oriented circle. And the parameter interval is from 0 to 1. Okay, so that one. And so you know that this is it moves counterclockwise and encloses A, and whose entire interior lies in this open disk. So the whole interior lies in this open disk, of course, right? So it satisfies everything for the theorem, okay? For the theorem system. So by theorem 14.4.1, so we have f and A is equal to n factorial 2 pi I gamma f of z minus A root to n plus 1's power and dz here. So this is from the theorem. So we have that. Okay? And now we take the x value. So we take the x value here. Okay, and then we have n factorial 2 pi here. So gamma fz v minus A n plus 1 and dz. Okay? We take the absolute value. Now, so by f of z we know it's an upper bound. So we have n factorial, capital M, 2 pi. Okay? And from 0 to 1, okay, and 1 over, when z minus a, z goes over the simple cross path. We have or e I 2 pi t n plus 1's power, and dz actually it's I 2 pi r e I 2 pi t dt. Okay, so the derivative. This is the derivative of gamma of 1 c. Okay, so we have that. And for all exponential terms, the f value is 1. Okay, because ei, 2 pi dt, they are all 1. And so we cancel 2 pi here. Okay, and r here. So we have this is equal to n factorial m. Okay, and r nth power dt. Okay, so finally we have. Right? So this is true, right? So this is less than that. Now, by linking, go to up to R, because this is true for only R less than capital R. So we let little r go up to R. So we have that less than equal to n factorial m. As nth power, and this is the result. Okay? Now we have an application of the Cauchy's inequality. Okay? This application is called the Liouville theorem. Okay, so Liouville's theorem says that every I forgot to define a complex function which is analytic on the whole complex plane is called an entire function. Okay, so an entire function is a very special kind of function that is analytical at every point in the complex plane. Okay. Now, the Liouville theorem says that every bounded entire function is constant. Okay. Okay, let me give a short proof. F is entire implies that F is analytic. So F is analytic on such an open disk for all center, this is 0, and radius r, this is 0. Now, since F is bounded, okay, on C, there exists an n greater than 0 such that Fc is equal to n for all z complex term. This means bounded. So entire means that F is analytical on all kind of open disk. Bounded means that we can find a positive number m such that the absolute value of the function value has upper bound here. So now by Cauchy's inequality, okay, just write, we have f times z0, absolute value less than or equal to m divided by r. Okay, so it's m divided by r. Okay, so m divided by r here, because n equal to 1, right? And n equal to 1, n equal to 1 here, and 1, Victoria is 1, and r 1's power. Now, by letting r goes to infinity, okay? So we have 0 for all z0 and c. Okay, so the development is 0. So this implies that f of z is constant on c. Okay, this is nothing to say about that. Okay, so the last result of this chapter. So we are very fortunate that I can finish all material. But I will give you another extra sections about the global Cauchy theorem. Okay, this global Cauchy theorem. So the following theorem is a converse of Cauchy's integral theorem. Okay, it's called Moreira's theorem. Moreira's theorem. Okay. All right. So omega, an open set. So my version is much more general than the version given in the textbook. Because in textbook, it states that omega is a simply connected domain. But actually, this theorem is true for any open set. Okay, the proof is a little complicated, but I give it to you in my. I'll send to you today, right? This section. So omega is an open state. Okay, and okay, for every closed triangle in omega, right? I forgot to say, and have continuous omega. Okay? So f is an open state. F just continuous on omega, right? And we require that the line integral of f of z, okay, along the boundary of any cross triangle in the open state. If this is true, then f is in omega. Okay. Cauchy's theorem gives you says that if f is an analytic, continuous, and analytic except one point, right? And then you can deduce that this is true for any cross triangle. Okay. That is the theorem 14.2.b, I think so. Is the Cauchy integral theorem for triangles. Okay. But we have a converse that f just continues. And if we can prove that this is true for any closed triangle, that this line integral is 0, then f is analytic. You can have a very strong result. Okay, so right, and the proof is a little bit complicated, but not very complicated. Just needs some statement. Okay, so I'll give you the proof. This version, because this version is more general than the version given in the textbook. Okay, so any questions? By omitting almost all proofs, okay, I can finish. But I hope that the general idea about the Cauchy's, especially the index, the winding number of the point with respect to a closed path, right? I hope you have a very, very clear idea about this concept. It is very important in complex analysis. Okay, with this concept, we are able to state the Cauchy integral formula. And because Cauchy's integral formula is the foundation for many results, including that we can prove that any analytic function has derivative of any order. Okay, that is and so that we can prove the Liouville theorems as well as we can prove the Morella's theorems. Okay. So I will put some effort to give you the global Cauchy theorem, because what I gave to you are just local Cauchy's integral theorems, right? They are just local properties, and so yeah, I would like to give you the global theory. Later, maybe you can use that later on. Okay, but it takes some time. But I promise you to give you the first section. This section is behind. Okay, I almost finished that. Okay. All right, and next week I will start with chapter 15. So before the weekend, I will send you the first sections about power series again, because we started power series in chapter 5, right? At the beginning of the second part, and then I write a heavy note, maybe close to 20 to 630 pages, right? Give you a complete introduction okay, on power series, okay? And so I hope you can read through that, okay? At least the statement without proof, okay? You can so we will rely on this material about the power series, the theory of power series, okay? And so and then we hope that we can finish chapter 15 next week, and then chapter 16 next week before the final examination. Good. All right. So see you next week.